Okay. So welcome everybody to the mini workshop. Yeah, so the idea was to give also PhD students a chance to talk and other people who would like to give shorter talks. And we found that maybe 2 hours is a good slot that works on a global scale. So we have 4 talks today. They should be 25 minutes and we allow for 5 minutes of questions. Yeah, as usual, if you want to ask a question, please raise your hand or leave the question in the chat. But we want to avoid too many interruptions. So whenever you're ready, Jakob, then you can go. So today, the first speaker is Jakob Muldoon, and he will talk about the Floquet Limbonian Dynamics of a lossy qubit. So please go ahead, Jakob.
Hi, everyone. My name is Jacob Muldoon. I'm a student studying at Indiana University, Purdue University of Indianapolis, or just IUPUI. As Andre stated, today I'm going to talk to you about Floquet Limbonian Dynamics for a qubit that is experiencing 2 different types of loss. So as part of my talk, I'm going to give a quick primer on what Limbonian dynamics are, then a primer on Floquet theory, and finally get into our simulation results. So what are Limbonian dynamics? Well, the idea is that if I have my universe that is described by some density matrix rho, S plus E, then the evolution of this density matrix is going to evolve according to the quantum Liouville equation, which is Schrodinger equation. I have that posted here. However, my environment might be quite complicated. I might have far too many degrees of freedom, far too many sources of noise in my environment. So I'm interested in removing those aspects of my system. So what I do is I partial trace over the unitary according to the degrees of freedom in my environment and obtain these Krauss operators. And then what I can do is look at how each of those Krauss operators update a differential time increment of the density matrix and use that to define a Lindbladian superoperator on the density matrix. So what form does this Lindbladian take? Well, there's actually multiple forms. The one that people are used to seeing is the operator representation, where both the density matrix and the the density matrix is represented by an operator, and the Lindbladian superoperator is represented by this equation. There's multiple points of this equation. You have a commutation with the Hamiltonian of the system itself, and that is going to result in coherent unitary evolution. Then you have this anti-commuting component of the Lindblad, and what that is going to produce is coherent but non-unitary evolution. And finally, we have this ending piece that looks like those Krauss operators from the last page, and this is going to result in decoherence of the density matrix over time. And we refer to it as the quantum jump operator. However, this form of the Lindbladian is somewhat difficult to utilize. It takes a little bit of trial and error in order to find the eigendensities. So instead, the form of the Lindbladian that we're going to be using today is the matrix representation, which we can utilize since it's a linear superoperator. We can just have it act on the elements of the density matrix itself. So converting it over to the matrix representation, it takes this form, and specifically we're using the convention where if I have a square density matrix, I'm going to stack the columns on top of one another in order to obtain the vectorized form of the density matrix. Now, having this form, I can define a eigenvalue problem with my eigenvalues of lambda. And the reason that we're really interested in these Lindbladian systems, even though this is PHHQP, is that I can add the anti-commuting part of the Lindblad into the Hamiltonian part and define a new non-Hermitian Hamiltonian that has a pure loss element. Then I can rewrite the Lindbladian in this form, And so we have what looks like a quantum Liouville equation for a non-Hermitian Hamiltonian. However, we have the addition of these quantum jump terms that are added into the equation. So if I had some way of removing the statistics resulting from these quantum jumps, then I would be able to simulate the dynamics of a non-Hermitian Hamiltonian. And there's a few ways that you can do this. So one way is that if a photon is given off anytime that your environment becomes excited, then you're able to just detect for photons in your setup, and anytime that you detect a photon, just stop data collection. Another way is that if you are working with an atom and you have 3 energy levels, a ground level and 2 excited levels, you can look at the upper excited levels as a 2x2 system, and then just detect if the atom has ever fallen into its ground state and stop data collection at that point. We call these methods post-selection. Now, the other aspect of our work is going to be Floquet theory. So with Floquet theory, I have some Hamiltonian that is periodic with some period capital T. I can define a unitary just normally according to the Schrodinger equation. However, I can separate that unitary into a complete period evolution and a partial period evolution. Now, this complete period evolution we call the Floquet time evolution operator. It's defined by this time-ordered product. And I can define a logarithm of that time evolution in order to define a Floquet Hamiltonian that is just a static Hamiltonian that will be working on the system. The last thing that we do is we take the partial evolution operator, split it into part of that Floquet evolution, and then a micromotion operator that is responsible for very short form dynamics of the system. Now, all of this is going to be repeated for Lindbladian dynamics, except for one major point, which I have signified by the question mark here. And that is that the Lindbladian superoperator has a few more requirements than a Hamiltonian does. Specifically, it has to be a completely positive trace preserving map. And for a Lindbladian specifically, it has to be describing Markovian dynamics. So there might be an issue in defining what the Floquet Lindblad is. However, I can still look at the full period evolution of the system. Now, let's talk a little bit about the difference between those two elements. So for the Hamiltonian, the Floquet Hamiltonian and the Lindbladian, there's going to be a description of the long time form dynamics, stuff that is going to take the majority of the evolution of the system in order to describe. The other nice thing about these one period evolutions is that they allow us to define a basis over their eigenstates that we can decompose the entire system into. The other part is, as I said earlier, the micromotion operators. These are all the little dynamics that happen over a single period of the Hamiltonian or the Lindbladian, and these are usually going to be averaged over an experiment. They're not really important for our talk. So before I get into the simulation results,
Jakob, Philip has a question. Maybe you go a slide back.
Yes.
Yes. Yeah, just go back to where you introduced the e to the tau. There it is. It would seem to me that LF is always defined as the logarithm of GT. So you must have some extra properties in mind.
Right here. Yes. So the big problem here is that you're not necessarily assured to get a completely positive map or that it's Markovian. That is the major problem with defining a static Lindbladian that is equivalent to the evolution, whereas with Hamiltonian mechanics, you're just always going to be able to define a Hamiltonian because it just has to be Hermitian. That's the only thing that you have to satisfy.
Okay, so are the conditions that LF be the way you've described it known?
Yes.
I mean, do you know how to take an arbitrary L and construct an LF that meets that rule, or are there L's for which that cannot be done?
So there are L's that it cannot be done for.
Okay.
Yes. In our problem, it's not an issue, but if you add detuning into our system, then it can become an issue. And you can have certain regions of parameter space where you cannot define even a completely positive map anymore.
Oh, okay, thank you.
Yep. All right, so before I get into the simulation results, I just want to explain what exactly we're looking at. So normally at this conference, when we look at phase diagrams, we're usually looking at regions where there's completely positive eigenvalues versus complex conjugate pair eigenvalues. We can't quite do that. You can see down here in the bottom right corner, I'll explain this graph later, but I want to use this bottom right corner graph. You can see that our eigenvalues are going to be distributed over values that are always going to be complex conjugate pairs if I define a Floquet Lindblad. So instead, what we're going to be doing is we're going to be looking at the modes of the time evolution operator, taking their inner products and removing the self inner product and looking at the maximum inner product that we get. So as the values go from blue towards yellow, they're going to approach an exceptional point in the Lindblad dynamics. And this is kind of a problem because, as I've got written here, even though the Lindbladian is a in its matrix representation is hermiticity preserving on the density matrix, it in itself is not Hermitian. You can have a few situations where the Lindbladian superoperator in its matrix representation will be Hermitian, but that requires that all of the Lindblad dissipators are Hermitian themselves. All right, so into our actual simulation results. So the first phase diagrams that I have to show you guys are for a periodic X drive and for a spontaneous emission dissipator. And we can see two different drive functions here, which I have described at the bottom of the page, the top one being sinusoidal and the bottom one being square wave. For the square wave, we have contours provided for the exceptional points. That is something that I'll explain at the end of my talk, why the square wave contours are easier to obtain. But the major things that we can see with this graph is we have a reproduction of the static version of this problem where the oscillation frequency is going to be 0. In that limit, we should have a Liouvillean exceptional point that is equal to 8J, and we see that reproduced up here. We also see that in the extremely high frequency regime, we have half of that as the Liouvillean exceptional point, which is what we expect. However, in the interim, we have these harmonics that are evolving, and these separate the phase diagram into two different sections. We have an underdamped section where I have one complex conjugate pair of eigenvalues for the time evolution, and then we have an overdamped section where I have completely real eigenvalues for the time evolution. Now the second phase diagram that we have, same exact drive. We're going to be using a sinusoidal drive. However, I've now changed the dissipator so that it is a phase noise dissipator. And the major thing that we see here that's different from the previous diagram is we have these regions where the orthogonality of the eigendensities is maintained. So all of the inner products along this dark blue line are going to be 0. Third, now we're switching to a static Hamiltonian and instead modulating our spontaneous emission. The big thing here that changes from the previous graphs is that we still have these harmonics. However, they're now only showing up on odd harmonics as an actual exceptional point. So all of these lines actually reach an exceptional point value. We can see that non-orthogonality is starting to maximize at the even harmonic values. However, it never reaches an actual exceptional point. Finally, we have the periodic phase noise diagrams. And the really interesting thing with these is that we have multiple exceptional points that are crossing in these diagrams, which allows us, as we just have small changes in our parameter set, to change from a completely orthogonal set of eigendensities to a exceptional point. Now, how do we obtain the exceptional point contours? So for the square wave solutions, those are going to be fairly easy to obtain because it's just two sections of the time evolution that we have to figure out. So what we do in order to reduce the dimensions of the problem is we're going to be looking at the expectation values along the X, Y, and Z directions of a block sphere. Then we can write those expectation values as a differential equation and look at its time evolution over time. So what we're going to do is that if we look at the time evolution itself, we're going to have a single element block that is associated with the X expectation value. And then the Y and Z expectation values have a block associated between them. That block is associated with the two complex conjugate pair eigenvalues for our time evolution operator. So what we do, since we're looking for the exceptional point specifically, is we want that 2x2 block to be proportional to the identity, because that's the point where the two complex conjugate eigenvalues are going to become degenerate. Once we set that block as proportional to the identity, we can obtain this equation, which has two different conditions here, one associated with plus sine beta and one associated with minus sine beta. The plus condition is associated with the black contours, and the minus condition is associated with the red contours. So just to summarize the results that I presented today, the Liouvillean exceptional points can extend all the way down to the Hermitian limit, so we're able to actually test our results with fairly low dissipation relative to our drives. And that can also be stated for the overdamped regions if we're interested in studying those. Beyond that, as I stated earlier, the density matrix is actually, the eigendensities are capable of maintaining their orthogonality deep into the dissipation range. And finally, we have the ability to quickly shift between our maximally orthogonal regions of parameter space to our exceptional points if we're interested in studying the encircling of those exceptional points. With that, I'd like to thank Yogesh Jobukar, who is my advisor at IUPUI. I'd also like to thank John Gunderson, who is an undergraduate student who helped us with this work, and Kater Murch, who supplied us with experimental expertise. I'd also like to thank the research group that I'm in at IUPUI. With that, I will take any questions that you guys have.
Thank you very much, Jakob. Questions, comments? No questions, no comments. I have a very simple one, and that is related to the numerics. How involved is the numerics you are doing?
It's honestly fairly simple for the square wave model.
Yeah.
For the sinusoidal model, it gets a little more complicated. But yeah, the square wave model is something that is really good intro research.
Because these problems quickly go out of hand and it becomes very involved numerically. So you do
Yeah,
this on a
if I
laptop?
actually,
Can you do it on a laptop? Yeah.
Hmm?
Can you do this, produce these pictures on a laptop?
I haven't tried.
Oh, I see.
I have a personal computer at home that is able to handle all these calculations. But
Okay.
if we actually look, you can actually see there's a bit of a fuzzy region up here in the upper left corner. And this is specifically due to numerical problems with floating point errors in MATLAB.
Mhm. The other question I have is your Hamiltonian depends explicitly on time, no?
For two of the well, not two of the slides that I showed today, yes, the Hamiltonian varies in time. Whereas the other two slides, the dissipators, are the ones that change with time.
Because when it depends on time and it's non-Hermitian, then it's actually not an observable. Because
Right, so that would be specifically if we're talking about non-Hermitian physics.
Right.
With the Lindblad equation, there's not as much developed there. Like, for example, I believe during Andrew Harder's talk, Carl Bender brought up that there's a problem with going over the exceptional point because now you're getting into a different regime of the eigenbasis and its commutation properties. But with the Lindbladian superoperator, we're not dealing with those like really nitty-gritty intricacies.
Mm-hmm. Okay. I mean, they're still there. It just means you don't see them, right?
Right. Well, there is one situation that we would be interested in using these to observe them, and that is the post-selection methods that I talked about right here.
Mm-hmm.
It's basically using these Lindbladian dynamics to simulate our non-Hermitian systems that we're actually interested in.
Okay. Any other question? Well, if there are no questions, then let's thank Jakob again. Thank you very much, Jakob.
Thank you, everyone. Sure.
And okay.